For the final talk, it's a great pleasure to introduce Markus Müller. Markus is at Institute for Quantum Optics and Quantum Information. He's worked extensively on many topics in quantum foundations, quantum information, and also has interest in mathematics. And today we'll be talking about reconstruction, space-time, and interpretations of quantum theory.
Okay, thanks very much. So yeah, first of all, thanks Philipp and Philipp for organizing this really great workshop. I enjoyed a lot. I was really sad that I had to skip the beginning because of a family emergency. So I hope to make up some of it and still chat with some of you tonight, hopefully. And thanks also for staying here so long. It's been a very long day, so I appreciate it very much. I will talk about quantum theory from simple principles. Certainly it's about reconstructions of quantum theory. I'll give you examples of how we can do it. But I will focus on one thing in particular, which I think is something where we can use reconstructions for. And that is to understand the relation between quantum theory and space-time a bit better. I also would like to say a few words, that was at least my original plan, about what we can perhaps learn from the existing reconstructions about how or how not to interpret quantum theory. Given that it's that late, I'm actually not sure if I get there, right? But we'll see. So here's an outline of the talk. I thought I begin, in fact, by reintroducing the notion of general probabilistic theories with some pictures and a little bit of a different language, because I think it will help a lot to understand some of the, I think, really nice insights that you can have once you have this in the back of your mind, what this means, like to have a probabilistic theory which may not be quantum. In the second part, I will talk about reconstructions of quantum theory. I will give you one example reconstruction with Luis Manzanes and co-authors, which is not necessarily the nicest or best one among all that exist, but I think it can clarify a couple of things. I will also mention new work by Howard Barnum, who's in the audience here. In the third part, then, I will show you what this could perhaps tell us about space-time. I will talk about two thought experiments, one pretty old one about an interferometer and relativity of simultaneity, one newer one from last year, and then probably the fourth part will not happen because it will be too late. But if so, I will argue that these existing reconstructions that we have put some pressure on psi-ontic interpretations of quantum theory, and I will try to motivate that it might be fruitful to do something that's like 80% on board with the cubists, but 20% not, because I like to think about private but objective probabilities, but we will probably not get there. But perhaps we can chat about this after the talk with a beer. Yeah. So general probabilistic theories, here's one way to introduce it and to visualize it. It's not the only way, but this kind of instrumentalist picture, you may think of a laboratory situation. We have preparations and transformations and measurements, perhaps given you in the form of devices, of procedures that you can perform. Think of, for example, a classical coin toss as a first example. You have a preparation device, and what you do is you press a button, and what it does is it kind of shakes a coin and maybe hands it over to the next device, perhaps hidden by a cup, like in a game. So say on every push of the button, this preparation device might just perform a biased coin toss. What the transformation device do? Well, it does something to the coin. It inputs the coin in some state and outputs it in another state, if you want to think of that. So for example, it might just invert the coin and move heads to tails or tails to heads. And then the measurement outcome is some procedure that gives you an actual outcome that you can see and record and communicate. For example, maybe this box flashes red when you have heads, right? Or green if you have tails or something like this. In this case, you could mathematically describe whatever comes out of the preparation device as a probability distribution, probability of heads or of tails. So you would call this your state, the state of the system that's prepared would just be a classical probability vector, P1 minus P. You could talk about the state space. State space is the set of all possible states that you could think a coin of being in, which can be visualized like this. So a fair coin would correspond to probabilities 1/2, 1/2. Very deterministic coins that always have heads or tails would be like 1, 0, 0, 1, and this would look like a line segment. Essentially a simplex in that. So that's state space of a coin. A transformation, if I said moves heads to tails and tails to heads, it would just switch the two probabilities. And you can see this maps an ingoing state to some outgoing state. And in fact, it's linear on the state space. The measurement outcome, say you have a device, it has a finite number of outcomes, and each outcome has a probability which depends somehow linearly on your state. And in the simplest case, where your device just looks whether it's heads or tails, and the probability of getting heads is just p, the first entry. And you can write this as a dot product with your state vector, essentially, right? So you have a state omega, and you pair it with a linear functional to get your probability. This scheme carries over also to quantum theory. If you have spin 1/2 particle, the preparation device, you would have a quantum state that describes the system that exits the preparation device. In general, it could be, for example, a 2x2 density matrix. Your state space would more look like a Bloch ball. So that's a parametrization of the states of spin 1/2 particle. Spin up and spin down would correspond to the north and south pole, but you'd have superpositions up plus down, for example, somehow on the equator, and the mixed states would be in the interior of this ball. So that's a very well-known way to geometrically visualize and parameterize a qubit or a spin 1/2 particle state space. What could be these transformations? Well, we could have, for example, a unitary transformation. You have some state omega, which is your density matrix. You map it to U omega, U dagger. That's what the transformation device might do. In this case, in this picture, it would mean that it basically takes your state on the Bloch ball and rotates it somewhere else. Could also be an irreversible map, a CPTP map. In any case, so a measurement in this case, again, so you say, maybe I measure, the measurement device measures spin, and then the probability to obtain a spin up, for example, on state omega would be given by the Born rule. And this is also some expression that's linear in the state, like in the classical case. So the general theme then is, when you have a general probabilistic theory, you have things that are called state. So what is a state in GPTs? A state is the thing that allows us to determine for all possible measurements, the probabilities of the possible outcomes. It's like a catalog of probabilities. Yeah, quantum theory, this is density matrix. And yeah. So what is a state space? It's basically the collection of all states that a given system could possibly be in. Different ways to interpret it. Let me just say it in this way. It's closed undertaking statistical mixtures. So for example, you can decide to prepare a state omega or another one tau at random when you toss some dice with probability 50-50. And then you can, if you want, express it as a convex combination 1/2 times one state plus 1/2 times the other. So that also refers to Ludwig's embedding theorem that was referred to earlier. And so you can, if you want, write these states as vectors in some real linear space. You can always do that. So this is what your state spaces could look like. They have whatever shape, they are bounded, they're compact, and they are convex because statistical mixtures of states are always states. In quantum theory, a system would be described by its Hilbert space dimension n. An n-level system would have the states that are the density matrices, trace 1 and positive semi-definite matrices. Classical probability theory of n outcomes would just have states that are probability vectors. Now, what is then a transformation? Well, it's something that maps an ingoing state to an outgoing state. Since it must play together nicely with statistical mixing of your preparation, it must be a linear map, right? And we call it reversible if it's invertible, and the inverse t to the -1 is also a transformation. Then you can, in principle, think of applying t, and then you apply t inverse, and then you've done nothing in total. And in quantum theory, transformations would correspond to completely positive trace non-increasing maps. The reversible transformations are exactly the unitaries. How do you describe measurements in the scheme? So you say, well, I have n outcomes, and for each outcome, I have a linear functional. And if I want to know the probability of outcome I just calculate ei of omega. In quantum theory, this would be the positive operator valued measures. The linear functionals can always be written in that form as the trace of some POVM element times the density matrix. Good. Now, it's important to see for what follows that the physical properties or information theoretic properties of a system depend very strongly on the shape of your state space. And this is a kind of nice example to see that difference. So you can think of the quantum bit, which is like a Bloch ball. So I've just drawn maybe the equator. Think of this as a bit, maybe a rebit over the real numbers, doesn't really matter. And this here would be a state space. It's like a square that's sometimes called a G-bit, a generalized bit. you can parameterize in that way. You introduce these coordinates x and y, and then you can ask, well, what kind of systems do I get? So what are the measurements? What transformations can I do if these are the state spaces? And then you can say, well, in both cases, I can imagine a measurement that I'm doing, some kind of box that gives me one of two outcomes, and I call it the x measurement. And the probability that I get yes on this x measurement is just the x coordinate, which is a value between 0 and 1. And the probability to get no is 1 minus x. Yeah. So these are valid probabilities between 0 and 1 in both cases, and they add up to 1. So I can imagine that there's a device that does that. And it turns out that it distinguishes, for example, these two states perfectly. Yeah. So if you have the device and you send in omega 1, you get definitely outcome no, whereas if you send in state omega 2, you get definitely outcome yes, for example. For the G bit, it would also do that for these two states, for example. In both cases, it turns out you can not distinguish more than two states perfectly. Yeah? There's no third state that could be perfectly distinguished in a single measurement. So when you say, like, suppose I have n states and I have an n outcome measurement with these functionals, and the probability if I set state omega j on effect ei should be either 0 or 1, like delta ij. This only works if n is 2 or less. Right? So this is why we call them a bit. You can only distinguish two states. That's why it's a quantum bit and why this is called a G bit here. Yeah. And both state spaces actually feature a notion of complementarity. So it turns out you cannot really know x and y simultaneously. In the following sense, if you think of the x measurement as one box and you think of the y measurement as another box, you cannot encompass them into like a joint device that reads out x and y at the same time. This is impossible in both cases. For the quantum bit, we kind of know why. For the G bit, if that was possible, then it could read out 2 bits of your state. I could distinguish this from that perfectly and this from that and so on. So I could have 1 out of 4 alternatives. I could distinguish that exactly, but this is impossible. So I have complementarity in both cases. However, here's something the Q bit has because it's a circle and the G bit doesn't, and that's uncertainty relations. So for the Q bit, if you have a state and the probability of this x measurement is either 0 or 1, yeah? So you know exactly whether you get yes or no for your x measurement. So you have one of these two states. Then for the y measurement, for the other one, you must have 50-50 probability. Yeah. So if you have these two states and you see the y coordinate is always 1/2. So knowing perfectly the outcome of one of the measurements tells you that you cannot know anything about the outcome of the other. And this is not true for the G bit. So for the G bit, you would not have this kind of uncertainty. The results of both measurements can basically be simultaneously deterministic, even if you're not possible to read them out at the same time. So here's what it could look like in general. So you can have a classical bit. That's what I've shown you. A classical trig would be like a triangle. So simplices are the classical state spaces. A quantum bit looks like a ball. If you've never seen a quantum trig, then it looks pretty complicated. Yeah. It's not a ball. It's the convex set of 3x3 density matrices. And it's a very complicated shape which has flat pieces on the boundary and very symmetric. It's actually 8-dimensional and very complicated. So don't confuse the set of density matrices with a set of complex state vectors. That's something else. But in general, you can have anything you like and describe like a conceivable physical system with it. So you can think of this landscape of state spaces or theories or collections of allowed state spaces where you have quantum theory, classical probability theory, and some of them are operator algebraic theories. We have a notion of multiplication of observables. Others don't have that, like theory called box world. Yeah, and then, you know, it's like a zoo of theories. It's a continuum of theories. And the idea is that of reconstructions is to find a small set of simple physical or information theoretic or other principles that singles out quantum theory uniquely in this landscape. And the role model is certainly to some extent Einstein's derivation of the Lorentz transformations from the relativity principle and the light postulate. Where also we had first a mathematically somehow complicated or unmotivated, certain perhaps description, and then it turned out you can re-derive that from very simple assumptions. Good. So now how can this be done? So I think we had in Philipp's talk already an example of a reconstruction of quantum theory. And let me now give you at least one more. So there's a long prehistory to that. I'm omitting many people that I should mention. Let me just say that a lot of what I'm doing is uses, for example, axioms that were used by Lucy and Hardy in 2001. Chris here was one of the first proponents that we should reconstruct quantum theory, and that this is something important to do. For the philosophers, they may know the CBH theorem by Clifton, Boop, and Halverson. However, what they do is they assume from the beginning that you have an operator algebra, and that's a bit like, yeah, like you want to climb Mount Everest, and then you're dropped off from a helicopter 2 meters from the peak or something like this, yeah? So, so ideally, you don't want to assume algebra, so any of the structure. And then some other groups that work on this. Philipp, we heard before, other people, Podivoy, Dakic, and I don't mention all of them. Howard also was here, and I mentioned some of his work later. Here's one reconstruction of quantum theory. Not necessarily the one with the most compelling axioms, but some of them help to set the stage for something we'll say later. So let's look at this. So this is a reconstruction from 2013 with Luis Massanes, Remigijus Augusiak, and David Perez Garcia. And we have 4 postulates here. Postulate 1 is called continuous reversibility, going back already to Lucy and Hardy. And it says that continuous reversible time evolution or continuous reversible transformations can in principle map every pure state to every other. Now, if you think of a spin state of spin 1/2 particle pointing in one direction, another pure state would be that points in another direction, then you can certainly find a unitary that moves it over. So one parameter group of unitaries from which you can transform one of the states to the other continuously. And here we say this should be true in general. All pure states should be reachable by every other in this way in general. Postulate 2 is called tomographic locality. So it tells us something about composition. So in some sense, it's a statement about what we even mean by a state of a composite system AB. And it says that the state of a composite system is completely characterized by the correlations of measurements on the individual components. We discussed a bit earlier whether that's really a necessary prerequisite for doing science or talking about subsystems. I agree with Howard that it's not, but I still think it's a very natural assumption to make. The assumption says the following. So maybe say Alice and Bob, the physicists, they are given a joint state AB of their both of their systems, and actually many copies of that state. And their task is to determine the state by performing measurements. Now, what tomographic locality says is all they have to do is do local measurements. Alice does local measurements and Bob, and then they correlate their outcomes, and this determines the state uniquely. In this sense, there are no holistic degrees of freedom that you could only measure if you bring the systems together. Postulate 3 is something we use here specifically. It's called existence of an information unit. So in this specific reconstruction, it tells us basically that we can encode everything into bits in some specific way. So there's a type of system, the universal bit, so that every other system that you have can be encoded into a sufficient number of these bits. Yeah. And you can also go back, right? And if you have 2 of these bits, they can indeed interact with each other in a continuous and reversible way. Now, classical probability theory does that almost, right? So you have an n-level system and a probability vector on it. You can encode them into log n bits, essentially, and go back. Quantum theory, you can do this with qubits. You can unitarily move over your state of a system to a sufficient number of qubits if you have finite dimensions. And here, this is an abstract formulation of the general possibility to do that without specifically mentioning classical quantum theory. 4th principle is called no simultaneous encoding. It was suggested by Anton Zeilinger some time ago, which says like a bit should really be a binary alternative system. Says that if one of these universal bits is used to perfectly encode one classical bit, then it cannot simultaneously encode any further information. I'll get back to that in a bit, what that means, right? In any case, what you can show is that if these postulates hold, and if you're within the framework of general probabilistic theories, then the state space of n of these u bits must be the set of density matrices of 2 to the n by 2 to the n Hermitian complex matrices, which are trace 1 and positive semi-definite, or linearly equivalent to it. And the reversible transformations are exactly the full set of unitary conjugations. So in this sense, it does give us back finite dimensional complex quantum theory. Now let's unpack this a little bit to get some intuition how that works. So for example, why are qubits balls? Right? Okay. Why not other shapes? And for that, actually, we need only 2 postulates, and you can derive it from many other assumptions. But here we need continuous reversibility and no simultaneous encoding. So first of all, what continuous reversibility tells you is if you start with any pure state, you can reach any other pure state with a reversible transformation. The reversible transformations form a group. It acts linearly on your state space. And so group representation theory tells you that you can reparameterize everything so that your transformations are rotations, essentially, orthogonal maps. So this tells you that your pure states must lie on the unit sphere in some real space of some dimension, and there's something like a maximally mixed state in the center. Now, perhaps this is the full ball, but perhaps a part of it is missing. So if it's the full ball, what can we do? Well, you have a ball state space, and then you can encode a single bit by deciding to prepare either a state or the antipodal state. And that encodes the bits, and that's all you can do. If it's not the full ball, then you can actually do more. You can say, well, if it's a 0, I'll encode the omega 0 state. And if it's a 1, I'll encode something on the other side of the state space. So maybe that or that or that, right? But you have more freedom what to do. So in addition to encoding this 1 bit, you can also make a choice to encode additional information if you encode a 1. And this violates no simultaneous encoding, right? So we conclude that we must have a ball state space. But why is it 3-dimensional? Why not d-dimensional for any other dimension? And for that, we have to look at the composite of 2 of these bits. So if you have one of these bits A and B, and then we ask, what about 2 bits? Well, what is it? It's some kind of joint state space AB. We know basically nothing about it. Just by tomographic locality, we can kind of count dimensions. So we know that the dimension of the state space must be d squared plus 2d. It's like d degrees of freedom here and d here. And so the correlations between them gives d squared, and the local degrees give like 2d. But we don't know what that set is. We know that it contains the independent preparations, which you can rewrite as products of states, but we don't know much more than that. But what we did was prove the following result. If you look at all possible dimensions of balls and all possible groups of reversible transformations that could possibly act on them, right? Like group GA, so whatever you can do to this ball, for example, all the d-dimensional rotations, but perhaps less. What could the joint state space be? Well, there are basically only the following possibilities. Only it's the trivial, so it could be the trivial composite. That means that you only have the product states and the mixtures. And the transformations that you can do on both of them are just independently doing something on A and something on B. So it's the group product of the 2 local transformations. Or the other case is that your ball actually happens to be 3-dimensional. Yeah, and the group of transformations on A and on B is like just the rotation group SO3. In this case, you get a new solution. There's something you can suddenly do, which is interesting, which is the unitary transformations on a quantum 4-level system. Yeah. And in fact, then the state space must be linearly equivalent exactly to the quantum state space. Right? So it turns out that in this case, a continuous reversible interaction of these 2 balls is really only possible if the dimension of the ball is 3, and if you have exactly 2 complex 2-qubit quantum state space. So this is, I think, nice. So this is quite constraining. And And now you can ask, well, why is D equal to 3 so special here? So certainly this is like complicated mathematical proof, but what's the gist of it? So then you can see, well, the place in the proof where dimension 3 becomes important is somehow in the proof you have to look at the rotation group of dimension D minus 1. Not D, but 1 dimension less. And you have to ask, what if I do that and rotate in all directions on some entangled state? Then you have to count how many dimensions you exhaust by doing so. And you get a far too big state space unless your group is commutative, right? So you need somehow that SOD minus 1 is a commutative and abelian group. Yeah. But rotations only commute in 2 dimensions and not in higher dimensions. And so this is essentially a mathematical reason why dimension 3 is special, because SOD minus 1 is only non-trivial and commutative for dimension 3. This is like the gist of the proof, and we'll see that again later. So keep that in mind for now. So there was a possible loophole of all of that was pointed out by Czeslaw Bruckner, who said the following, that's probably Duckage, said like, somehow we have assumed that pairs of bits can interact and talk to each other. But could we have a world where pairs cannot talk to each other, but when I have 3 bits, they can suddenly talk to each other, right? And then Czeslaw said, well, yes, there are now all these new theories that show up here. If we make this, if we drop this assumption of pairwise interaction, but Marius and I showed in 2019 that nope. So no new theories show up. And even if you just assume n-wise interaction of n balls, you also still don't get more than standard complex quantum theory. And then it was funny because there was a lot of like media reporting on it, and the Standard wrote this here. It's like, in a hypothetical world, quantum computers would be quote unquote boring. In more than 3 spatial dimensions and with more complex bits, quantum computers would not be more powerful. So that's a kind of questionable way, not quite wrong, but one way that the story was told here. Yeah. But this is what makes, I think, really Bloch ball dimension 3 special from an information theoretic point of view. Here is a new result by Howard, who's in the audience, and Joachim Hilgert, that I find totally compelling, partly because I've tried to prove it myself with Howard for a while and then alone for a while and never succeeded. And I think you should all read it, and it's underappreciated. It gives you another reconstruction of quantum theory, which does not talk about composition, but only about single systems. There are 2 versions of the paper, one of them a Journal of Lie theory, and another one on Archive. Not sure which one is better to read for the audience now. Anyway, so let me tell you roughly what it says, and then you can correct me if I say something wrong. What you begin here is you say, if I have a collection of pure and perfectly distinguishable states, let's call them a frame. So in quantum theory, this would just be orthonormal states, an orthonormal basis, orthonormal system. And then you have 2 postulates. Postulate 1 says that every other state can be written as a convex combination of some frame states. Yeah. Whatever state omega you pick, you can decompose it into such perfectly distinguishable pure states. In quantum mechanics, there's nothing but the spectral decomposition of a density matrix. Someone says like every state lives basically in a classical context in which I can see it as a classical mixture of the alternatives in some sense. Postulate 2 says that every 2 frames are related by some reversible transformation. So in quantum mechanics, this means that every 2 orthonormal bases are really related by a unitary map. Someone tells you all these frames are dynamically equivalent or something like that. And from only that, you basically get quantum theory. So the only general probabilistic theories that satisfy this are quantum theory over the real numbers, the complex numbers, the quaternions, 3-level octonionic quantum theory, and then these qubits or spin factors of arbitrary ball dimensions. So these are the formally real, simple formally real Jordan algebras, and the classical theory is missing here. No, is it? Yes. Classical probability theory also does that. Yes. Did I overlook something? Was it? Okay, great. Another nice result by Howard and Cosmin, actually, and John van der Wetering is you can also get, with a single system postulate, these, well, essentially these state spaces from what's called like self-duality and, sorry, You can get it from homogeneity and pure state transitivity. Pure state transitivity is, again, if you have a pair of pure states, there's a reversible transformation where one maps one to the other. Homogeneity is a statement about the mixed states of your system, that you can basically map every mixed state to every other with if you want irreversible transform. Well, no, this I think you have to explain. With a reversible transformation as well.
Yeah, I mean, I think in probabilistic terms, the best way to say it might be that every state that is in the interior of the state cone, so it doesn't rule out any outcomes, sort of a non-exclusive state. You could go to any other such state with a probabilistic reversible transformation.
Yeah.
So you know you can go there with some probability it's not zero, and you know you can get back with some probability it's not zero, and in each case we know that happens. So that's sort of enough. Otherwise, you can say the automorphism group of the code maps transit here.
So yeah. I think that the thing to emphasize is here, like this starts from GPTs where you don't have any algebraic structure, but you can derive Jordan structure from these postulates. That's the cool thing. Good. Now, what about space-time? Let's look at these bit state spaces again. So a qubit is described by the Bloch ball, where just the 2x2 density matrix in state vectors are parametrized by a 3-ball. But certainly you can think of ball state spaces of any dimension as describing your bit. And this also goes back to Jordan von Neumann and Wigner, who realized this. So here are the first few cases. So if you have a 3-dimensional ball, this is like the qubit for quantum theory over the complex numbers. If it's just 2-dimensional, then it's like its equatorial plane. So this would be like quantum theory with real amplitudes. A classical bit is also a ball. It's a 1-dimensional ball. It's like the coin that I've shown you. 5-dimensional ball would correspond to quaternionic quantum theory, but it could be any dimension D in principle if you look at a standalone system and ignore other postulates that are written down and just say maybe something is described by that, like some kind of bit. Again, as I said, a Q-trit and so on is not a ball. So all of these are bits. You can only ever distinguish perfectly one state from its antipodal state and not more. You can ask, well, why is D equal to 3 in our world as far as we know? Well, we've already seen an information theoretic derivation of this fact, but here's another one that has to do with geometry of space, in fact. So this is a paper with Andy Gardner and Oscar from like already a couple of years ago, where we consider something like an interferometer. So this is something like a Mach-10 interferometer, where you say you have two alternatives. A particle, whatever that is, could be either in the upper or in the lower branch. And whether it's up or down is basically a binary alternative. So you can describe it with one of these d-dimensional Bloch spheres. You can describe its state where it sits, was a state on this Bloch sphere. So one interpretation would be if it definitely sits in the upper branch, this would correspond to your North Pole state. Definitely in the lower branch would correspond to the South Pole state. Right? If it's somehow on the equator, then in the middle, like between North and South, then you would have a state, whatever that means, where when you look and you measure, then you find probability 1/2 of being up or down. That's what the GPT framework tells you. So the probability of being up here would be 1/2 times the Z coordinate plus 1 of this ball. Why can I say that? Well, because it must be linear in the state, as all measurement outcome probabilities are. Good. Now I can ask, well, suppose there's a physicist, Alice. She's sitting there and she wants to do something to the particle. So perhaps she puts a little piece of glass inside the interferometer. So you think of that as a transformation that Alice does. And you can ask, what are these transformations that I can think Alice to do here, that she performs locally in one of the arms and reversibly, so without any information loss? Well, in this case, since it's a reversible transformation, it must somehow rotate your Bloch ball. And since it cannot signal to the other arm, it must preserve the probability that the particle is sitting here. So it must preserve the Z coordinate, right? Because that's related to the probability that the particle is here. Well, so you can see what this does. If it preserves the Z coordinate, then it must be a rotation that preserves this axis. You can also think that Bob is in the other branch and is also doing something like that. Right? And if you now say, well, let's assume, if you assume that this is the only restriction and no other restrictions apply, that what you can do is all rotations of dimension d minus 1, right? So whatever Alice and Bob can do is described by the group SOD minus 1. Good, but now suppose we're in Minkowski space and you fly by, your friend flies by with a spaceship and looks at your setup and says, oh, wow, hey, first Alice is doing something and then Bob is doing something in the setup. But then your other friend flies in the other direction and says, no, actually first Bob is doing his transformation, then Alice. And then you should say, well, both descriptions are valid. So relativity of simultaneity tells you it shouldn't matter how you describe the situation. What does it mean? Well, it means that the effect of first doing TB and then TA must be the same as if you first do TA and then TB. Right. Since you can do this for all these rotations of the Bloch ball, this must be true for all rotations SOD minus 1. Well, so SOD minus 1 must be a commutative group, right? And so D can be at most 3. So this is a bit surprising because even here we assume that we have kind of dimension 3 for the Bloch ball because SOD minus 1 is non-trivial and commutative only for D equal to 3. But wait a second, we've seen that very same mathematical reason to apply in the information theoretic reconstruction. Right? So I think this is cool. Yeah? It kind of hints at something, some deeper core that's common to both, like to information theory and space-time. There must be some relation and something we can study here that relates these two, yeah, in the way that they have something to do with each other. Yeah. You can, in fact, like make this more rigorous. I've skipped some steps. You can say, well, maybe instead of saying what Alice and Bob can do are all these maps, they can just say, let's say whatever they can do are just isomorphic as groups. And then you get that the dimension could also be 5 and that quaternionic quantum theory also survives as a solution. So in the end, you can cook up a theorem. You say, here are my assumptions about what the beam splitter does and what I can do to the arms. And then you get a theorem that tells you the only dimension of the ball 1, 2, 3, and 5 are possible. And these are exactly the qubits over the associative division algebras, which you get from relativity of simultaneity here. Okay. So this was part 1 of space-time and structure of quantum theory. Part 2 is a newer work from last year. Which I will only sketch, which will take a long time to properly introduce, but here's the idea. So it's based on a semi-device independent randomness generation scheme. So what does it mean? Well, it means you have a casino in Las Vegas, you want to generate random numbers, and you want them to be secure and private. Right? So essentially, you say, here I have in my lab some kind of quantum experiment. I get outcomes B. I can have a setting X. And it looks to me as if the outcome would be unpredictable and random. But I want that it doesn't only look for me as if it was random, but even an eavesdropper that knows more than I should have trouble predicting the outcome. Yeah. So you can think of a situation where you have a preparation device which takes an input X, sends a physical system to a measurement device and produces an outcome B. And you want B to be unpredictable given X, but you want it also to be unpredictable given all other hidden variables lambda that an eavesdropper could know. Yeah, so this guy wants to rob your casino and he knows all these details about the air molecules in your casino and how it fluctuates from run to run. So what you think is your state is actually a convex mixture of some other states that this guy knows, but you want still your outcome to be unpredictable even with this additional classical side information so that the end conditional entropy is still positive. And you don't want to trust your devices because you bought them from the NSA. And then you can do that. So there are schemes that allow you to do this. All you need is like an assumption on the physical system. So this is not like completely device independent, like a Bell scenario. So you need to make some assumption about what's transmitted here. Typically, the assumption is, oh, this is really a qubit. And then you have 4 settings here for a qubit, and then you cannot perfectly distinguish it. It's really random. But what we do here is we replace this by a bound on the spin. We say what we send has to respond to spatial rotations in a certain way. And our input to the preparation device is either doing nothing or rotating the device by some angle alpha. I can ask, well, if I do this, yeah, and I say, maybe I assume this is a spin 1/2 particle, I have 2 settings, 2 outcomes. Instead of the probabilities, I can look at these correlators. So there's 1 correlation for each input, there's E1 and E2. What kind of correlations can I actually get? So you can plot them. So it's E1 and E2. And depending on what angle alpha you fix and what you believe about the spin J, you can work out what the possible correlations are that you can get on your experiment. And then you can prove first within the formalism of quantum theory that here's an inequality that tells you which correlations you can get. Basically, it's this blue set here. Yeah. It tells you, for example, if you don't rotate by too much, then you cannot get these corner correlations, and they would mean that the states encoded here are both orthogonal. So you rotate just by a little angle, or you don't. If the spin is small, then these 2 states cannot be orthogonal, and you cannot perfectly distinguish them deterministically, and these correlations are impossible. Right? So this is the kind of analysis you have to go through. Forget the details. When you ask how many private bits do I get, then the shape of this set of correlations is the thing you have to look at. Point is, you first can look at quantum theory, derive it, and get this blue set. And then you throw away quantum theory and say, let's do it without assuming quantum theory. And it turns out you get exactly the same set for all J. So we don't need to assume quantum theory for this protocol to work, for getting the set of correlations and for having guaranteed randomness. And this has to do with a way in which quantum theory is somehow optimally tied to space-time transformations. And here's a slide about what that means. So it's a bit similar when you think of a Bell scenario, where you can have quantum correlations or more general PR boxes. And here, there's a scenario where you rotate your device. And you can also ask, what's the quantum and what's the more general bound? So here's what I mean by a quantum spin J box. So you have an angle alpha, a continuous parameter, and then you have outcomes plus or minus 1. Yeah, and you ask, what probability tables can I get? Yeah, if the probabilities are just given by the Born rule. By the Born rule, and it's a rotation by alpha, so it must be a unitary representation of the rotation group. In this case of SO2 rotations, because I rotate around a fixed axis. And when you say here in this picture, well, I want to say that the spin is less than or equal to J, then this gives like an upper bound on the representation label, like what's in these representation matrices. It can be at most e to the ij alpha, basically. It tells you how you rotate your state. Consequence of that, for example, is that the probabilities are always a trigonometric polynomial of degree 2j. So if you spin 1/2 particle, then the way it acts to responds to rotations might just have that form here, like 1/2 plus 1/2 cosine alpha or something like that. So you might well think of something like post-quantum or more general spin J rotation boxes, where you're not assuming that your states are density matrices, that the rotations are unitarily represented, measurements are PVM operators. You just assume you have any state space, whatever that is, where the rotations are linearly represented with highest rotation label J, or 2J, in fact. Akkustand ist niedrig. Okay. That's good. It means I should probably not do it too long here. Right? And then what you say is, well, essentially, you can have any kind of trigonometric polynomial of degree 2J. Yeah, that's kind of all kind of spin J rotation boxes you could have. So you can put these two side by side and then compare them. And you can say, well, certainly the quantum boxes are a subset of the general rotation boxes. And then you can show, well, for spin 0, they are the same because it's just constant probability. For spin 1/2, they are also the same. It's kind of straightforward to prove that. For spin 1, they are also the same, which is terribly complicated to prove. It took us a couple of months. But for spin 3/2 and higher, they disagree. So suddenly for spin 3/2 and higher, there are more general ways in which nature could respond to rotations than allowed by quantum theory. And we're just writing this up at the moment. But for small spins, you kind of see that quantum theory already gives you the most general possibility. And if you say that instead of allowing the continuum of all angles, you just have 2 fixed input angles, then the sets are the same. And this is what makes our protocol work here, when we either do nothing or rotate by a fixed angle. So here's an attempt, like a kind of tempting conjecture coming from that and other thing. Like, is quantum theory perhaps the unique probabilistic theory that fits reasonably into space-time somehow? Or is there some elbow room for beyond quantum physics? Could there be regimes in physics in which it's not described by Hilbert space, but that would still play together nicely with transformations of space-time? I don't know. Maybe not. That would be exciting. Maybe there are few possibilities how it's possible. That would also be exciting. It would be nice to find out. So I think that the reconstruction methods and program can and should be used to study this. This is kind of nice, I think, and interesting. And there's certainly historical precedent when you say the success of quantum field theory can be seen as the success of the desire of combining special relativity and quantum theory. So somehow space and time on the one hand, and then the probabilistic aspects of a theory on the other hand. And perhaps, this is very speculative, this is hinting at something like this, where you say, there's an unknown fundamental theory because something that we want to talk about when we say quantum gravity. And in some approximation that applies to the regime that we can at the moment probe, it reduces on the one hand to general relativity of continuous space-time and also to quantum theory. And then it's kind of clear that they must play together and perhaps show common features if something like that applies. But that's certainly speculation, but I think it would be nice to study that. Good. How long have I already spoken? Not sure how much time I have. So I have a few minutes? Okay. Yeah. So nobody has yet fallen asleep. I get to the fourth part now. Interpretation. I think quantum theory is a theory of probability. That's at least my takeaway from the reconstructions. And that's something that Czeslaw Bruckner already said in 2014 in Vecchio, in some nice words, where he said that the very idea of quantum states as representatives of information that is sufficient for computing probabilities of outcomes following specific preparations, has the power to explain why the theory has the very mathematical structure that it does. This in itself is the message of the reconstructions. And I think I agree with that. I think it is remarkable that starting with a framework where you try to describe in the most general way possible probabilities of events and the correlations allows you to derive this formalism is very suggestive. We wrote an article about this where we kind of put down this thesis here, and some of it is maybe not that important anymore, but still, just to say it again. So this was with Adam Koborinsky, who was a philosophy PhD student at that time at Rotman. So the thesis was that information theoretic reconstructions provide a sort of partial interpretation of quantum theory as a principal theory of information, or maybe not of information, but rather of probability, I would say today, by identifying a small set of information theoretic principles that render our world a quantum one. And this leaves several alternatives for extending to a full-fledged interpretation. Furthermore, the reconstructions represent a challenge for existing psi-ontic interpretations of quantum theory by highlighting a sort of relative deficiency of those interpretations in terms of the explanatory power. Right. So quantum theory, so what we were referring to was kind of Einstein's distinction between principal theories and constructive theories. It's something that I don't find that important anymore, but that was the main idea, that in this reconstruction way, you get quantum theory as a principal theory of probabilities. And so indeed, why is it now a pressure for psi-ontic interpretations? We said we think of its explanatory power as sufficient to pose a challenge to proponents of more traditional psi-ontic interpretations. None of Bohmian mechanics, Everettian quantum theory, or collapse theories fill the explanatory role of a principal theory. For example, Everettian quantum theory does not start with a broad general framework of theories of many worlds and then put simple principles on top of that and proves that quantum theory is the unique theory of many worlds that satisfies these principles. Right? So you begin with probabilistic theories, write down simple principles, you do get quantum theory. Nobody has written down a landscape of many world theories, some principles, you get quantum theory. And certainly we're not the first one to say that. Chris has said that before. Well, even much before this paper, I think. What Chris and Blake Stacey said, that the point is far from being an appendage cheaply tacked onto the theory. The idea of quantum states as information has a simple unifying power that goes some way toward explaining why the theory has the mathematical structure it does. By contrast, who could take the many worlds idea and derive any of the structure of quantum theory out of it? This would be a bit like trying to regrow a lizard from the tip of its chopped off tail. So the Everettian conception never purported to be more than a reaction to the formalism in the first place. I think that's beautifully put. So my personal takeaway is I do agree with the cubists with that. And also, indeed, that we should think of these probabilities that the framework talks about as private or relative to some referent. We can think of that as an agent or use of quantum theory because of arguments that we've already heard from the cubists, having to do with non-locality and with Wigner's friend. So this, I'm all on board with cubism. And I think one could stop there and say the reconstructions themselves don't tell us much more. We can be agnostic about what kind of probability that is and then stop. I'm not stopping there, but I cannot justify this by reconstructions alone. So this is now really something where I want to say I deviate from cubism, and I'm basically saying that because I want to have a beer with Chris and Rüdiger after that, and with Matt and yeah, with all of you. So in contrast to qubits, I think that the notion of agency or free action is not necessary to understand the characteristics of quantum probabilities. So at first you might think it is necessary, and that's very suggestive when you think of Bell experiments. Certainly you can only have non-classical correlations in a Bell experiment if you think of Alice and Bob freely choosing their setting, deciding to do one measurement and not the other. The point is not so much that a random number generator could do that for you, but there's a free decision. But then there's this other work on more general causal scenarios, like the triangle scenario, like Tobias Fritz wrote about this. This was actually version 1 of his paper. For some reason, he changed the title in version 2 and didn't say anything about it anymore. So he says, here's a scenario, for example, a triangle scenario where you can get correlations that you cannot have classically, but you can have them quantumly, and nobody chooses anything here. So this is a hint for me that maybe agency and choosing is ultimately not as important to understand quantum correlations. Here's another point of deviation from cubism. First of all, I see yes, it's a very natural choice. So it seems natural to identify these private probabilities that are relative to an observer, for example, with subjective degrees of belief. Because when we think of everyday life, when is a probability relative to an observer? Well, if it's their belief. Otherwise, if it's the chance of raining tomorrow, it wouldn't be observer dependent. That's how we typically think of it. But then the price to pay is that they have no on-take hold on the world somehow, and that you have to work on really making the connection that you want to make to say something about reality. So the suggestion here is that we could instead think of these as private but objective chances. Why do I want to do that? Not a priori, right? So if you say I want to interpret quantum theory, then you could just be a cubist. Or if for some reason you really, really want to be a realist in a very classical naive sense, then be an Everettian and deal with all the other problems you have with it. But here's something you could do if you take the other view of something like private objective chances. So begin with a question like this. So we ask what will probably happen to me next? Now, you can say two things. First, maybe you can say, well, I see quantum theory as a motivation to regard this question here, this question Q, as more natural than asking what is the case in the world. So a measurement, when you do a measurement, we get an outcome. We shouldn't think of it as uncovering a fact that has been there before, but I go with the cubists in this case that it's about predicting future experiences. So that's the motivation of quantum theory. But then the crucial thing is that there are these other enigmatic instances of this question Q that people discuss in other fields, and that I think would make sense to make contact with what we do here. And these are kind of enigmatic instances of this question. We don't know how to answer this question. That's, for example, the Boltzmann brain problem, where you think you're part of a very large universe, and you want to predict what you see next, and your answer should depend on the cosmological model. So I don't want to go into the details and chat about this later. Another question would be the computer simulation of agents. Somebody proposes to simulate, like scan and simulate you in a while on a computer. Well, should you expect to find yourself in a simulation or not? So what will probably happen to you next? There are some other philosophy puzzles. The common core of all of them is that we do not know how to derive probabilistic statements from assumptions about facts of the world. And we want to answer that. And so that's, yeah, so that's what I said. So, and then the research program that I would want to suggest, and that's why I would want to take this idea seriously, is like that instead of interpreting quantum theory, try to build a framework that answers this question Q in all cases, and ideally predict some aspects of quantum theory in some situations. So that would be something I would like to do, and I do elsewhere, and I'll stop here. Just suggest this as something that I think could be done. And yeah, that's a summary, but yeah, thanks a lot for your attention.
Thank you, Markus, for an amazing talk. Questions?
Well, thank you. That was great. Can you just go back one slide?
Yeah.
So a reference.
Yeah.
So, I mean, since you were just contrasting your view with cubism, I mean, obviously cubism would agree that you cannot derive probabilities from uncertain facts of the world. It's the whole reason why cubists just think about coherence and not about actually deriving the correct probabilities.
Yeah.
So, can you just briefly comment on that?
Yes, so I think standard physicists would claim that you can do that, and that's what you typically do in some sense. When you say, like, here's the situation is the following: I go to the lab, I put this laser here, this detector over there, and I want to predict whether I hear the click or not. Yeah, then you would at least say, well, I can use quantum theory to give me a probabilistic claim about the matter of fact that has to do with the optical table, and that predicts whether I hear it or not. Right? So I would think that the way we typical physicists think of quantum theory is along that line. Or even classically, when you want to predict the weather tomorrow, then this is more clearly obviously the case. That the standard method is so there's this world sitting there, and you predict how it evolves and assign probabilities to it, and that's your method to predicting whether you will feel warm tomorrow. So, yeah. So, good. Not sure if where are we now? It's already 7:15.
Okay.
Sorry.
I mean, yes, that's the usual view, but that's contrasted by what you're saying here, namely that it is unclear how one actually can do that. I mean, people think they're doing it, but my view would be that there are always assumptions that come in which cannot be derived from the facts of the world. So, would you agree with that, or?
Yes, I think I would agree up to that point. I would still say that it makes somehow sense to claim that there is something true to saying that there's an objective chance of you hearing a click or not, in some sense. Maybe not as an actual numerical probability floating around in the world, right? But maybe as a kind of statement about, given what you know now, this is what you should believe, right? So this kind of thing. So I think more than the cubists, I'm more like sympathetic to the idea of some notion of objective chance. Yeah, that's probably the difference. Probably Richard Healy would also be a bit more in that direction. So we should probably talk to him. Yeah. Yes.
Well, I learned a whole lot from your talk. But at the moment, you're going to laugh at this. I'm thinking the great innovation is begin with the question, what will probably happen to me next? And the why I think this is something of an innovation would be for us, not you're already there, is successively lately I've become more and more uncomfortable with the way we cubists express that a measurement outcome is a personal experience. Because it seems natural enough if you're talking about persons. But if we get into the tangle that Stefan wanted us to go into earlier today, where there's 160 scientists at CERN or at the LHC, and there's so many computer programmers and so forth. It caused me to think of the introduction to Savage's book, where he says this book is about a person, how a person makes a decision. And then near the end of the introduction, he says, now it could be that it's a whole organization that is doing the gambling and making a decision about what is best. Even in this case, I'm going to call it a person. So it's an organization of 162 people plus 40 programmers. And in Savage's decision theory book, he would call it a person. And in a way that diffuses the issue, because, well, that seems perfectly natural. Now, what changes in the quantum theory case, I think, is that the measurement outcomes too are personal. So we adopted some old philosophical word experience, mostly because David Mermin liked it. But if you just say it in this sort of neutral way, what I'm gambling on is what will happen next to me. What will happen to me next? It sounds like, doesn't sound so wild. It sounds like a very simple concept. And now the me could be the organization of 160 people plus 40 programmers.
Right. Yeah.
So anyway, I really like that formulation, and I think I also dig the that's a 60s term.
Okay.
I dig wanting to embed quantum theory in a much larger set of considerations to do with nearly everything.
Okay. Okay. Nice. Yeah. Thanks.
So I have a follow-up on Chris's comment that the me. So Chris says that me can be an organization, but I'm pushing it in the opposite direction. Can me be a particle or a non-living entity or the environment? Or does it have to be a conscious being?
So certainly now you ask, so there's this suggestion for doing this, and then there's a specific way. I've already put out a suggestion elsewhere. The way, how I suggested was to say the me is fundamentally something immaterial. It's the pattern or structure that you are, whatever you are, right? It doesn't have to be a person or a human or anything. It doesn't even have to be a structure that's smart enough to actually use quantum theory to actually calculate probabilities. It's something, so think of something that contains data and collects more, some abstract version of that, right? So in any sense, I think there's already a point of departure that I think when I think about objective chances, then if it's not subjective degrees of belief, then it doesn't pre-assume that you're smart enough to do calculations, to use quantum theory or probability theory. You say, I'm something and something happens to me. And if I were smart enough, or somebody else, some hypothetical third party that observed me could then predict what will happen to me. Right? Yeah, but this is perhaps also for another day, and you might have different options how you want to pursue this. Some of them may have stronger or less strong overlap with cubism, I think. Thank you.
We have time for one last question.
This is unrelated to the last part, actually, surprisingly enough, considering I'm a cubist. But about the spin box example, I got a little lost, but I came back in at the end. Were you basically saying or was the conclusion at the end that through Hilbert space dimension 3 or 4 or up, I guess starting at 4, then there started to be a deviation from from like the completely general.
Yeah, let me show you the slide. So here, so in quantum spin J box, you say
starting in dimension 4. Okay.
Starting in dimension 4, but also see that I don't fix the Hilbert space dimension to begin with. It could be a reducible representation, which is high dimensional.
Oh, okay. Oh, yeah.
But after like 1 or 2 pages of calculation, you can prove you can indeed realize it all in dimension 2J plus 1, right?
Okay.
It's just not presumed. And indeed, and then somehow it's been 3/2, which is dimension 4, you see a difference. It's kind of interesting because we think the elementary particles are all spin 0 and 1/2 and
no
1.
idea if it's going to be related, but there's also like another thing that we like to study that dimension 4 and up is where it starts getting interesting. So
Okay.
I'm just wondering if it's the same thing.
Maybe, yeah.
Oh, you have.
Okay, thank you so much for this talk. This was super interesting, and I guess what we all saw is why Philipp and I thought that this should be the first talk of the conference, but we are super happy that we could, hear this. So this relates to Rüdiger's question. Maybe you answered it right, but it's late and I'm tired. So probabilities, right? You say you would prefer a version where you say probability of objective probabilities. And maybe you have answered this question, but objective in what sense? Objective in the sense, outward nature, it's a fact of nature that this and that can happen, or like objective in the Coxian sense of probability theory in contrast to the Feletti Bayesian probability theory. So what could you say more about the nature of probability, about this objective nature of probability? Is it more like ontological or is it more like epistemic? Epistemic in the sense I should, quantum mechanics tells me by virtue of probabilities what I should believe to experience next, or what I should believe, or is it more in an ontological sense, like this is also
well, sort of ontological, but then I'm a mathematical physicist to want to de-emphasize this distinction to begin with, right? So the idea is somehow not to claim that there is an actual well-defined numerical probability 0.47 that I hear this click and this is out in the world and that's the right probability, and not in that naive sense, but enough of objective probability to say, given that I'm now this observer with this particular situation and knowledge and so on, there is some sense in which it's truly more likely to see the sunrise tomorrow rather than not seeing it, right? And then you have different options how to express it mathematically. One option would be by a collection of priors. We say these are reasonable priors. It's up to you which one you choose, but here's a rule how you should update, and it should not give you probability 0 for sun rising tomorrow and so on. So it's a bit of a longer story, but something along that line, some claim about something being actually more likely than something else for you privately.
Okay, this will help. And regarding this question that Chris brought up, like you mentioned in this fundamental question, according to you, what will happen to me next, something like this, right? So Chris pointed out that he likes this phrase a little bit more now than previously. Cubists might have said something like, what I will experience next. Is there a reason why you put it this specifically, like what will happen to me next instead of what I will experience next? Or is it just, contingent, this is just what came Which seems plausible to you as the distinctive reason why you prefer the notion of happened to me over the notion of what I've experienced.
There is a motivation for that, and that's in some sense. So certainly this embeds into like a larger project where I don't have time to talk about now. And I don't want to go too much into the details how you would want to play this out, but you can think of it's not only your experiences that are kind of determining who you are and what these probabilities might be, but also maybe memories and unconscious things. And so think of even if you don't have an experience, you might have something that happens to you. So experience is like the most clear and simple instance of that you might be sleeping and then you forget something, or you make an unconscious experience, like an unconscious record of something. So the way I say it is all very human-centric and colorful. So certainly you have to ask in the end how do you implement it mathematically somehow. And as soon as you want to implement it mathematically, then you have to be abstract enough so that what you do is not restricted to any specifically human notion of experience or qualia or some high-level notions that you would want to focus on philosophically. And it's more technical then. It's more like information theoretic approach. And that's why I like to talk more about what happens to you rather than what you experience.
Okay, thank you.
Okay, so let's thank Markus again.